Okay, hello everyone. Am I audible?
Yes, sir, you are audible.
Okay. Within few minutes, after 1 minute, we'll start the session. Let the other people also join. Okay, so let's start now. So this session is our first revision session. Okay, for the end term. And today session we'll try to
Professor,
Noel.
sorry,
Yes.
Professor. I just checked out this mock exam paper. I noticed that
Mm-hmm.
it's mainly about the last 4 weeks content.
Mm-hmm.
So
Yeah.
is that uh, will the final exam exactly like that or?
Yeah, that's the mock is actually, you can say, the template of interim, and kind of the question would be, if I will divide the portion, like we'll say the percentage wise. So the more emphasis would be from week 9, 10, and 11, 12, and the percentage wise it would be, approx 65 or 60 65 will be, the question would be covered from these sections, week 9, 10, and 11, 12, and the rest all 40 or maybe 35 would be from week 1 to 8, as we have done quiz 1, quiz 2. So questions already asked from these sections. The remaining sections are 9, 10, 11, 12. So more emphasis would be on that.
Okay, thank you.
Yeah. Okay, so let's start now the session. Let me present my screen. So in this week also we'll try to cover 9 and 10. 2 weeks we'll try to cover. We'll revise the concept of week 9 and 10. As the rest, we have only two revision sessions. So 9, 10 would be covering this today's revision session, and 10, 11, and 12 would be covering the next revision session. And yeah, we have already quizzes done and revision sessions are there already. So if you want to revise those, so you can watch us to recap the revision sessions of quiz 1 and quiz 2. That is going to be same, right? Just that is also a kind of a recap, so you can watch it on YouTube. That's why usually we record it also. It's available on YouTube. So it would be good even if we just recap the this 4 weeks with these two revision sessions. So first revision session would be for 9 and 10, which I am taking, and the second revision would be on the next as it is scheduled, and will be taken by, I think, Srikanth, and week 11 and 12 we will discuss that. So in today's session, we'll discuss the mock problems if you have. Otherwise, I have some slide. I will discuss that. Uh, I have taken the questions. It could be from activity, practice, or from anywhere of this 9 and 10. We'll discuss, just quickly recap the whatever the contents are there, topics are there in week 9 and 10, and related question to that. So let me present my screen. I hope my screen is visible to all of you. So as we see, sorry. So in week 9, topics are, we have seen in week 8 and previous weeks, integration we have seen. So in week 9, the application of integration is there, and then length of arc we have, you know, and some diagrams like area of the circles or some number, improper integral also. That is a kind of application, you can see it, improper integral. And then computing the volumes of solid, how if you revolve with respect to x-axis any function, if you have any graph of any curve, sorry, if you have a curve, if you revolve with respect to x-axis, what is going to be the volume within that, and logarithmic functions. So these are topics in week 9. And in week 10, the complex number started. Some arithmetic is there, like arguments or maybe absolute value. And then complex plane is there. Then sinusoidal functions, and then polar coordinates, sine functions, cos function, and how we'll convert to, or if we have a coordinate system, how we'll think that too in the coordinate systems, derivatives of sine, cos function, and one most important topic, one question, sorry, the thing is the Euler formula. And some trigonometry identities are there. So these are topics in week 9 and 10. So let's start to very quickly recap of uh, week 9. So if you see it, their application. So we have know that integration, which is nothing but the a kind of Riemann sum is there. Okay, and we used to take the limit as n goes to infinity. Means we have some interval, and we used to take the partition of it. Okay, and whatever we have the curve, we used to partition, or means within some interval we want to find the uh, we want to integrate that, so we will partition we'll take the partition of it, and then corresponding area within that partition, and we'll sum them slowly. That is a Riemann sum. No? Dividing the region in small pieces, and then calculate and sum them up. That is a Riemann, but Riemann is converting to, we'll take the limit of that. We'll do the partition very small, even if you say as n goes to infinity. Means if you have interval a to b, we'll take the partition of a to b minus a divided by n. And according to that, we'll take the function's value and the partition height, how it is. I hope you know the Riemann sum we have detailed in discussed in the previous weeks. So integration is a part of taking the limit as n goes to infinity, so that sum become as integration. So if you have a function fx, okay, and I want to uh, integrate this function between some interval a to b, so that is called area within the curve. We have this is a and this is b. We have the graph of function is this one. So integrating a to b is, we are saying to be we are taking the region, or what is going to be area behind the curve. That is the one thing. And not only this one, we can even think of different shapes. Let's say I have this very, suppose you have a field which of this shape. By sudden, suppose you have a field which of this shape. I want to find the reason. What is the reason of this? What is the area of this reason? Okay, so somebody said that okay, the whatever the boundary is there, this boundary can be given by a function fx, and similarly this boundary could be given by another function gx. If you have this information, then you can easily calculate. It's not a kind of a very usual rectangle or a square shape or circle shape, or as we standard shapes we have usually find, we can easily find the region. But I suppose it is not as the regular shapes we have. So in that case, uh, suppose this kind of shape of the region is there. So I want to find the area of this curve. So by sudden, suppose somebody is given that okay, this boundary have this curve kind of means graph related to this fx, and this one is for gx. Okay, so now can you calculate the area of it? So in that case, we generally follow what is that. The simple step is that we can think, okay, let's say this is uh, okay, this is cx. So you can say, okay, we can easily calculate by the way of, we can calculate first the area under the curve fx, and then we can find also the area under the curve of gx, right? And then we can subtract. This is how the meaning of the whole region from the whole part, we subtracted this part, and then you will get the region of this one. So, so it means to find this one as if let's say this is your uh, A and this is your B. So you can find the full region for fx is this one, and for whole region to B is sorry for gx is this one, and the subtracting to be like this. So better to be in place of doing this, we can think the area within the curve is going to be integration a to b fx minus gx, and then outside gx dx you can write. So this is how the one application is finding the area is which uh, with the region is bounded by two curves. Sometime it could be of this case even. So let's say this is going to be this. Let's find the area of this one, where the starting portion here is given. Let's say it is given here somewhere a, but you don't know about the ending or the other side. What is that? Suppose the field is of this shape. So to find this, simply if suppose this is your fx and this is your gx. So what you will do, you want to find the intersection, so you need to solve these two curves. Means so sorry, you solve these two functions. I means here the point is here. It tells you that here both values are same for fx and gx. So you can solve by both are same. So you will get an equation you can solve, and you can get the value of x, and that is going to be the point here. Let's say you got x is equal to b there. So now you have the boundary of, you can now easily calculate with the same method area under this curve, and area of the area under this curve, and the area under this curve you can subtract. So this is how the meaning of. So related to that, I have one problem here. This one. So I want to find, and so the question is, A is area isn't bounded by the curve these two. So what is going to be the 6 times the area? So all of it right, let me know what is going to be the answer. So what I am discussing here is that clear first.
Yes, sir.
What I said clear. Okay, so let's do this problem. All of you try once. Anyone got the answer? Quickly it can be done, right? Because we generally we are doing on in exam, then we have to do in a fast way. Anyone got the answer? Levis is saying, is it one? I don't know. Anyone got the answer? Others? Have you done this? So let's do it. So here is the region bounded by the curves is given here, 4x square and then mod x. So if you draw here, the mod x we know generally, this is how it is. Okay, this is our mod x. And the another is this parabola, which is 4x square. So here it would be of this case, it will go like this only. And it said that region bounded by the curves. So these two curves. So here bounded by these two regions, sorry, these two curves is this region, right? This is the region we have, and another region is this one. So here we have this 0, 0. We want to find this intersection point here and here. So here doing this is not enough. One thing if you see it, both are exactly going. These two curves are symmetric with respect to the y-axis. If you see, these two curves are exactly symmetric with respect to y-axis. Even this one or your parabola, both are exactly the symmetry. So if you calculate only this region, it and do the twice of it, or I mean to say this region, area of this region and area of this region both have the same area. So want to find the whole means if it is A, area is let's say the total area for this area you got B, and this is also going to be B because of the symmetricity, and you can do just twice of B. And if you want to verify, you can see it if you solve this. If you're assuming to be, I want to find the even intersection, no? So let's equate it both. 4x square is equal to mod x. So let's first find the intersection of this one, this line. So this side is just saying to be x, and this is 4x square is equal to x, where it is going to be. This is going to be, you can take as 4x square minus x is equal to 0. So this will give you x. You can take common. So this is going to be 4x minus 1 is equal to 0. So either going to be x is equal to 0, which is here intersecting already, and the second one is x is equal to 1 by 4. And this is going to be 1 by 4. So here is 1 by 4, and you can calculate the second coordinate easily. And now you can calculate the region between 0 and 1 by 4. And here is, this is just line x, and the below line is 4x square. And if you integrate it, this is going to be x square minus, this is 4x cube by 3. Okay, and this is 0 to 1 by 4, it will go. And this is going to be now 0, we substitute, it will be 0. And this is going to be just 1 by 4x square minus 4 into 1 by 4 cube into 3. So this is a square. So here the calculation would be, let's say here it is. So 1 by 4x square, 1 minus 1 by 3 kind of. And this is going to be, this is just calculating, you can calculate what is there. So this is 3 minus 2. So this is 1 by 16 into 2 by 3. This is 8. So this is 8 by 3. Sorry, not 1 upon 24. So this reason is 1 upon 24. And if you do twice of it, no, we have to do twice of it here. So here it is going to be 2 into 1 upon 24, which is 1 by 12. And it says find the, so total area. So total area we got this one. This total area is 1 upon 12. But it says 6 times a. So 6 times a is 6 into a, we got 12. So this is, I think, 1 by 2. Somebody says 1, I don't know. I think I'm then making mistake. Is it correct? Anyone can unmute and tell. Is this numerically correct or I make mistake?
I think it's 1 by 8.
1 by 8.
Yes, sir.
1 by 8.
Yes, sir.
Okay, this is 1 by 8. I think I am making mistake somewhere then. This is 1, 3, 2. Yeah. Yeah, this is 1 by 8, no? 124. Okay. I think maybe I made mistake here. So I mean to say that numerically you have to go correctly, otherwise. But the whole meaning of doing this is this one only. So let's do the next part quickly. So next concept is length. If you have a curve, okay, if you have a curve, so what is going to be the length of the curve? That is the second concept, second lecture. If you have this function, I have this, I want to find, let's say even, some rope is there, okay, some rope is there. I don't know of, and there is some hanging rope is there between two poles. And between two poles is, you can get easily, but yeah, okay, no issues. Want to find the length of this rope. What is going to be the length of it? Somebody is given that, okay, this representing a curve y is equal to something, some y is equal to something. So what is going to be? So we can easily calculate by the integration. This is one kind of again the application. What is going to be then? Anyone can tell the formula? Suppose we have a fx curve, we have fx. What is going to be length of that between a to b? Anyone can give the formula?
Yes, sir. Under root of 1 plus f derivative x square.
Square needed there. And then here
And then you will take
integration
the limit a to b.
Limit a to b, and then here dx. This is what it is. So any curve would be given. What we have to do? We have to first derivate, and then once we derivate it, and then square them, add them, find the root of, and then finally integration a to b dx is there we have to. This is that's all in the finding. So this is one application of integration, is a kind of it. So even let's say I have on one problem now, I have this one. Again, it is boundary problem. Even let's do this. So it is solving to the region bounded by these two curves, but I want to even perimeter. Yeah, this is good. So okay, this problem is, this is the problem we have, the second problem. So here I have two curve, this one and this one. I want to find area is we'll do later. Well, I want to find the whatever the region we got. Okay. This is the curve we have, and this is another curve we have. I want to find the, let's say, this shape. I don't know what is going to be the shape, but I got this shape, suppose. So I want to find the perimeter of this region. What is going to be perimeter here? This kind of question would be asked easily, no? So suppose this is your fx and this is your gx. So I want to find the perimeter, means you have to find first intersection between them. You have to find the boundaries, means sorry, endpoints. Once you find the endpoint, then you can easily calculate, no, this length of this curve. Again, the formula using this way: integration a to b root of 1 plus f prime x to the square and dx. And to this, to get this one, you can do plus integration again a to b root of 1 plus g prime x, derivate it and then square it. And this is how you can get the perimeter. So
Can you repeat,
let's do
please?
at least the upper part. Yes. You want to say something, someone?
So can you repeat, please?
Need to repeat. Sorry, you're saying?
Yes,
I
sir.
didn't get clear. Okay. So here, for this problem, it's asked a perimeter. So separately, we have to find this curve of this length and the curve, length of this curve and length of this curve separately. So this is fx. So we have to first find the intersection. So for example, let's say, let me graph this curve. So here is, we have this x square minus 1. X square minus 1 means here the graph would be, it is going to be, if you substitute 0, it will be off. In this case, it will be off. This is x square minus 1. The second one is this x square plus 1. So x square, minus x square plus 1. So if you draw, we have the x square plus 1 is this one. Graph is, if you graph it, this is going to be somewhere like this, but it is a minus is there. That means the reason is going to be inverted. The graph, it will be inverted roughly here. Ask the perimeter of this region. Okay. Perimeter of this region. What is going to be the perimeter here? What is going to be this? The red one. So how we can calculate? So we can easily calculate. We have to first find the intersection here and intersection here, and then we have the formula. Finding the length of the curve is, this is our gx and this is our fx. So separately find the length of the curve between, let's say this is here a and this is b. So integration a to b and root of 1 plus g prime x whole square dx. This will give the length of this portion here. And now to get the second one, you can do the same, apply the formula with fx. So it is integration a to b 1 plus root of fx square dx, and then sum them. That's all it is. So nothing is more. Only just need to follow the formula. I can even I thinking to skip this and this solve problem. Otherwise, even you want to find the intersection, let me do that. What is the intersection point here and here? So you just need to equate it to fx is equal to gx, and this is going to be x square minus 1, and gx is minus x square plus 1. So you just send it to there this side. So this is x square, sorry, 2x square, and this is minus 1 is equal to 0. Or here you can see it, this is going to be x square is equal to 1 by 2, or you can say separately x is plus minus 1 upon root 2. So that means here this is going to be 1 minus root 2, sorry, minus 1 upon root 2, and this portion is going to be 1 upon just 2. And the y coordinate you can get it. What is that easily? So this is, or mean to say here it is, this is here minus 1 upon root 2, and this is here 1 upon root 2. Now you have to integrate between the so which is in formula y is minus 1 upon root 2, 1 upon root 2. This portion will be, you can keep it here, and this portion you can keep it here.
Sir,
Is this
excuse
clear?
me.
Yes.
So that would be
Yes.
2x square minus 2,
Sir, yes, sir. It will be 2x square minus 2.
and we'll get x as minus 1 and plus 1.
Oh, sorry. Okay, this is, so this is 2. Yeah. This is 2. Then it is going to be 1, and then it is going to be plus minus 1. So sorry, this is going to be minus 1, and this is, yeah. So thanks. Yes, I just made a mistake. So just need to integrate it. Yes. The calculation part is I'm just leaving to you. Okay. So these two things are there, length of the curve, and these are again the entire, sorry, application. And next is improper integral, because other things are area of the circle, pi numbers, perimeters. Perimeters is just now we did, so perimeter is the area under area of a circle. So the next is improper integral. So area under the circle is area of the circle is the how the formula is generated by r square, or others is one application of the uh, integration. Let's move to the concept which is improper integral. Improper integral is a kind of integration which is of this case. Let's say I want to integrate a function fx is equal to, sorry, is 1 by x, between minus infinity to infinity. Even I don't know if this will converge or not, or I am able to integrate this or not. Even this looks like I am keeping the limits are infinity minus infinity. Sometimes the limits are not indefinite. It could be a definite, but it's we have, like, let's say I am saying this one, integrate this function between 0 to 2. This is also a kind of improper integral, because the reason is here 2, it's behave like asymptotes, this function. So this is a kind of improper. Improper means you cannot just integrate and substitute, will not give the value. You have to follow a different procedure. So how we can get the procedure, or how we'll get that? So where is the improperty is that let's say here it is as this 2 as 2, it have the function have a kind of behaving not properly. Okay, so what we can do, you can assume that portion as t. Let's say you can do without saying to be this, you can assume this is just a t, and you can think that this is limit t goes to 2. And then So mean to say you will first evaluate this limit, sorry, this integration as the simple thinking as t as a finite number. Oh, that is a finite number, but the case is that t is goes to 2 means what? We have discussed now. T is goes to 2 means t is not 2. T is not equal to 2. T is somewhere around 2. It could be very close to 2, but not 2. So we can integrate because now this integration could be done. This is true for any other, for any except 2. This is true for any real number. So we can evaluate. Once we find this integration, and then in place of doing or substituting 2, you can substitute t, and then take the limit of as t goes to. So this is how we will deal with the improper integration. Either of this case, 1 upon of x. So if we want to evaluate this, so we can first assuming to be, let's say this is this integration, or we can exactly convert this integration as t goes to infinity and then integration 0 to t 1 by x dx. So now you all, let's find this integration first. So this is going to be limit. So first find this integration. This is integration of 1 by x is what? What is going to be? Anyone? Log x, right? Natural log, I think.
Yes, sir.
So this is natural log. So limit t goes to infinity. Natural log is here ln x, and even infinity 0 and t. So see, this is not only improper with respect to infinity. This is improper with respect to so for this limit 0 also, because log function is not defined 0 at 0. So this is kind of improper with respect to 0 also. So the thing is that the integrating the function fine, but the issue is where the function is improper, really behave. So here this is a kind of improper function, improper integral for both numerator, sorry, this upper limit and lower limit. So you can say first saying to be, you want to say, so it is the surely this limit is not exist. It is very obvious, because how you'll find, if you find the first find the upper limit with respect to this, even log x, sorry, log t, log ln, what is going to be the limit as x goes to infinity ln x? This is just infinity, right? As the log function is increasing, so this limit is not definite. Even for 0 is also going to be negative, so it's very much obvious it is not exist. So I mean to say, this is what it is. The improper integral is somewhere the function we having a particular point, at a particular point we have like an improper, the function is improper at that point, and still we want to find the limit of that. Generally it is of this case, we have generally it's we have like asymptotes, or maybe if there is a break, there, but still we want to find the limit between 0 to that break point. Let's say this function is fx. So at b, the function is a kind of improper, but I want to find the limit as upper limit at there. Still we can calculate, because sometime, not sometimes, if this limit is exist, if this limit exists, whatever we are discussing, then yes, totally fine. The limit exists means finally we got the improper integration. So not only this, sometimes it's actually here, this region you can easily find. Still at b, the function is behaving improperly, but you can find the region behind that. Integration is finding the reason behind the curve. So this is what it is. The concept of improper integral is this one. I think there is a question I have taken or no. Okay. Questions are there, we can even I have discussed with an example even 1 by x. That's enough. We cannot discuss whole within 2 hours. So next is we are slowly moving to the. So before to move to the next topic, anyone have any doubt on whatever we just now discussed in these three topics?
Sir, can we do one example?
Yes, we can do one example. Let's say, let me create one. Let's say I have this integration. I want to find integration of, integration 1 to infinity, and this one. Find this. Yeah, I think it is fine. This is the integration we have. So let's say I have this function. Let's say I'm clearly writing here f(x) is equal to ln x upon x. Okay. So find the integration of this function. So all of you try it. Let me know what you are getting here. Anyone have solved this? Is this limit exists that improper integration is exist for that? I think let me see something. Log x. Indefinite. Okay. I thought maybe it will exist. Okay, maybe this is okay. Let's do this. So we have this limit, so we can assume as this limit t goes to infinity 1 to in 1 to t. Our function have ln x upon x and dx. So here to solve this, we know, right? We will use the substitution. So we can assume this is ln x is u, then this is going to be 1 by x, dx is equal to du. So this is going to be limit t goes to infinity. So here, okay, so we have to do the change of limit also. So this limit is going to be now, we substituted here for x is 1, so substitute 1, so log 1 value is, what is going to be log 1? Log 1 value, anyone? 0?
0.
And if you substitute for t, so this is ln t. And here is going to be 1 by x dx is going to be have like du, and ln x is just u. So u du will get here. Oh, so yeah, this then yeah, we have on travel now. Yeah, limit is not going to be existed here. So this is going to be, let's see what is going to be. So finally limit t goes to infinity, this integration is u square by 2, and this is 0 to ln t. So and at the last we will finally substitute the limit. Okay, this is how it is. So this is going to be ln t square by 2, and 0 will substitute, it will give 0. So this is what we will get here, and this is limit t goes to infinity. We got. So here I thought maybe this will exist. So this is what it is. So here we know that this log function is increasing function. So we want to find t goes to infinity and of this portion. So anyhow this will go infinity. So limit is not exist here. So this integration is not a definite. This is indefinite integration. We didn't get a proper integration here. In place of this, I should do some different even, then we'll get. But yeah, this is how we'll proceed. This is the full step to proceed. Let's move to the next problem. Okay. Logarithmic function. Log functions. So we'll discuss this problem, but let's just start. Log function is, even professor started from the log, is from the integration. And as a case of antiderivative, is saying that antiderivative of 1 by x, right, is going to be a ln x. So log whatever the base is there. So mean to say, even to be here, or differently I will say, we have an exponential. We know e power x or any kind of exponential where a is any positive real number. Okay, exponential we have, and this exponential are actually invertible always. So whenever we have a this function is increasing, so it have the inverse generally. So inverse of this exponentials are actually logarithmic. So like we have let's say I have a 2 exponential here, let's say 2 power x, and another exponential 3 power x. So inverse of this exponential is called logarithmic, and to denote that it is called log, and to represent this is log base 2, and this is x. And this one is log of this case, to recognize that okay, this log is inverse of this one. So that's why the base word is there. So this is a base and this is x is there. The variable would be there. No? Just generally you have the function fx and then variable is there. If gx is inverse of it, or even f inverse of it. This represent your, you can say, a kind of log. And to recognize that this is the inverse of exponential 3, so this is 3 is there, and x is as usual, or you can write like this. So log is built it and of the inverse of exponential, and this is how it is. Or in, so this is why the base concept is there. Okay, base 2, base 3, because it tells you that this is the inverse of this exponential, this is the inverse of this exponential. So this is the logarithmic we have. So here is one beautiful property. We can see that if you have written log, okay, a to b, and sub c is there. So this equation you can think is in the exponential form is also. So whatever the base is there, it will be the base, and this portion is your will be the power. As here, see, whatever you are getting value here, whatever the value will get, that is going to be the output here. Sorry, we'll substitute there, right? So or mean to say here, it will be more visible to here. So that is here, and this is going to be a power c is equal to p. So mean to say you have a logarithmic, you can convert that to this fashion. a power c means you can convert this to in exponential. It is very much obvious how it's happening. If you did here a power c, you got b, right? If you, let's say you did 2 power 3, you got a, right? So if you want to convert this in logarithmic, so that means you got this to 8. So you can think this is log, I am doing on the base 2, so base 2 8. So what it means that this is inverse, right? This output one I am substituted in the inverse function, so this will give 3. This is what you see. So this is a relation originally, if you able to catch it, what I mean to say. Otherwise this is a relation to convert the logarithmic in exponential. This is important. So that means if you have a log with base a and you have a power some again the a power of, let's say this alpha. So this is nothing but alpha time log base a, and which is going to be just, now if you have a log with base and a value is going to be 1. Here this is going to be alpha. So this is another property of logarithmic. And if you see the graph wise, we have seen the exponential function is this one, a power x, where a is greater than 1. So logarithmic graph is going to be, this is how it is, symmetric with respect to the line x-axis. Sorry, x is a line, y is equal to x. See, this is what the symmetry is happening. Whatever how the function we having lying with respect to this line, see exactly the logarithmic we having like that way. So this is your log base ax, here is exponential of a power x. So these are some relations, exactly it's behaving. So if you see it here, this is how it is. This is the log ax, symmetry with respect to line y is equal to x. So these are some logs, and some other properties are there. So logarithmic functions are increasing. Okay, so let me write the list out the all. This is increasing. Okay, other properties, if you have log with any base a, b plus base c, so this is log of base with same base a and bc. And if it is division is there, so this is going to be, sorry, if it is a subtraction is there, so this is going to be divided by, so this is b by c with the same base. So if it is addition, then multiplication would be there. If it is a subtraction, so division would be. These two properties are there. Some other important property is that if you have log with the base a, b, here it is. So you can write this, you can change the base. You can write base a and then. And another thing is also log with base a and b is there. You can write this log with separately base on the base 10. No, you can write as these bases are as become the argument and base become 10. This is one beautiful application also, that you can, any base you have, you can convert that into a base log base 10. Changing, this is change of bases. So there are some specific logs are there. Log base 10 is there. There is a log with base e, exponential one, no? That e, which is written as ln, and this log 10 is just written as log without any base. And except these two, base would be surely written. Getting it, all of you, what I am discussing here? Wants to
Yes,
say
sir.
something? Is it better? So these are some properties. So using this property, we'll discuss something more. So let's say some even a derivative of it. what is going to be derivative? So derivative, as the came logarithmic started from the antiderivative. So if you have a log function, so derivative of this 1 by x, integration is as the antiderivative is there. So I have this one problem using on the properties of it. So like this one. So we have two function fx. So the problem is which of the following options are true. We have this function. So we want to derivate it, that what is going to be. Yeah. So this is one good thing we have. We have any base fx is there. What is going to be derivative of it? Anyone can tell if you have a base, what is going to be derivative? Any base is there, then what is derivative?
It will be a to the power x ln a.
A to the power x. So here is going to be a to the power x ln a. ln a.
Yes, sir.
Is it this one? Means log base e, you are saying. And then a is here.
Yes, sir.
Okay. So to do it simply, one thing is there. So here it is going to be this one. Okay. So if you have any base, then the base become means any base. If you want to derivate, so derivate is going to be as here a power x, and then it is going to be. Simple example is that if you have e power x, if you derivate this, you will get exactly e power x. If you apply here, is going to be the same. This is e power x, okay, and here is log base e, and here is e also. So e going to be 1. So finally you'll get e power x. So this is correct here. We can verify it. So this is what, if you have any with any basis there, so we can derivative of it is going to be this is. So if you have log a function of fx is equal to log of base a x is there, what is going to be derivative here? Anyone? Anyone can answer? No? So here the derivative is, you can think this is, if you don't remember, if you remember only this is log with base e is going to be 1 by x. So here is base is anything. You can convert this to, with base e. So this is ln x and this is ln a. In that sense, you can convert. And now you can derivate it. So this, the above portion is going to be 1 by x, and this is, we have a constant. So this is ln a, or in more precise form, this is going to be 1 by x log with base e and a. This is what it is. This is how you, by this way you can remember you. So 1 by x is going to be here, there same. Yeah, in multiplication some constant would be there, and which is log with base e, a is there. Okay. So here are some options are there. So we did on this a power x, so we can easily do which option is true. This is there, this is there. So composition is going to be what? And if you have inverse and gx, then what is the limit? So see, this fourth option is a bit interesting. So fx is 1 by x and gx is log x. So fx into gx is going to be log x by x. And what is the limit when x goes to infinity? What is going to be here? Anyone can tell what is the limit here as x goes to infinity? Is 0. So is like going to be exist or any different thing?
It will exist
It is 0. It will exist.
It would be 0. How it is 0?
We'll use L'Hopital rule.
because x grows faster than log x.
X grows
Yes,
faster than.
in that way also you can justify this as x
Hmm, hmm.
grows faster than log x.
Yes,
Or we can use the L'Hopital rule, derivating the log x and x, the numerator and the denominator, and then put the limit x tends to
limit. Yeah, I think L'Hopital is start, no? So here it is be having. L'Hopital is there in the course, right? Let me
Yes,
check
sir.
this. Derivatives, then I think it is there. So L'Hopital is there, says that the numerator, if going to infinity, denominator is also going to separately goes to infinity. So in that case, just the limit existing saying to be this is saying to be the limit of just derivated the above portion and derivated the denominator also, numerator and denominator, which is 1, and then find the limit of it. So this is going to exactly saying be whatever the after the derivative you will get. So this is 1 by x. This is going to be c. So this is a L'Hopital rule. L'Hopital rule is, so it says that if you have a function fx and gx and is written like this, so the cases is that if both going to 0 or both going to plus infinity or both going to minus infinity as simultaneously, okay. So in that case, the limit saying to be as x goes to infinity or x goes to some particular point, just derivate that. So means f prime x upon g prime x, limit of at a particular point or infinity you want to get. So derivating that and then this is L'Hopital rule. So using that easily, or in the different method, if you observe this is the numerator is ln x and denominator is just x, and this is going to be much faster in comparison of log, because if you see the log graph is slowly like this now, and if you see the denominator graph is going to be, see how it is, this is exactly this way. So denominator is going to be very fast, where log is now slightly flatter. It will also go infinity, increasing, strictly increasing one, but very slow. And if it is a very slow and denominator is very fast, so finally it will go to the denominator will be embedded here more on this portion, and if this goes to infinity means 1 upon goes to 0. Okay, so these are some properties of logarithmic function. Okay. So let's move to the next topic. There is a one thing, computing volumes of solid. This is again one formula is there. I will just recall the formula. This is the formula. Again, as the finding the length of a particular curve. So you have a very specific formula, integration a to b, that root thing. Now, similarly, if you have a curve, okay, and you want to revolving with respect to x-axis, let's say I have this curve, you revolved. So this is going to be this like this. with respect to x-axis. So whatever you are getting the shape, what is going to be volume of that? So to get the volume, exactly finding the integration from this point to from where, and means integration a to b, then pi time the function whatever you have, square that and integrate that. This is the formula. This is a formula. Okay. So logarithmic and some applications are there. So I think applications like this is the curve on the revolving with respect to x-axis. Okay, we have this curve and it is revolve with respect to x-axis between, okay, revolve with respect to x-axis. I want to find the revolve even between x and x1 to x5 about x-axis, and it is says the volume, if the volume of the revolve by this about x-axis is this one. Okay, it said already the volume is this one, then find the value of k, it is there. So means here the volume is already given. So here is we have a function. If you see it, the graph, the function is this one. Let's say it's like this, maybe somewhere, but it says between the x and to x for x5 means I want this portion only. The curve is like this, and I want to this portion only 1 to 5, and it is revolve with respect to x-axis. So this is the roughly shape you will get here. What is going to be volume here? So to get the volume here, directly we'll use the formula integration where from where to where it says. So this is 1 to 5. Pi time, the square is there. So fx square dx. This is the going to be volume. So v is equal to integration 1 to 5. Pi you can make it out. And this is x square minus 4x plus 5. And the whole square dx is there. You just need to expand and integrate one by one term wise. You can easily get the answer. Okay, so this is the volume thing. So is this clear? Whatever I am discussing wants to say something or not clear or anything? Am I audible properly first?
Yes, sir.
Or there
Yes,
is a...
No, sir. You are audible.
Yes.
Okay. So so this is all about week 9 is there. So these are the topics. We have 2 hours only, and within that we have to complete it. So this is just a recalling. No? These are the topics there. So these are the topics we doing to be, this is just a recall. We are revising the concepts. We have to move a bit fast. So this is all week 9 is there. Let's move to the week 10 contents. So in week 10, slowly move to the complex numbers are there. And then sine functions are there, an Euler function, and the inverse of the sine is also there. And some trigonometry identities are there. So in week 10, we have complex numbers. And then some what is going to be conjugate, arguments, planes, complex planes are there. These things are there. And then sine functions, the main thing, the sine function is there, sinusoidals. And then inverse of it, sine inverse, cos inverse. The third is Euler formula. Okay. And then some identities, trigonometric identities. So let's quickly see one by one. So complex number is, the simple reason is how it's generated. Again, I am saying that we started thinking of this case. We know, right? We have a polynomial. So if you want to find the solution of this polynomial, you will say that, okay, if you substitute x is equal to 1, you will get 0. So x is a rule there. But the case arises when this is the x plus 1 is equal to 0. If this is you have, what is going to be solution? So here now the real numbers fail. Here the real numbers are fails now. You don't have any real number which have this, where this polynomial have any root, or this equation have any real solution. So now the complex number comes in pictures, and from here you can say we took something is there. I mean to say there is no real number, so which have this solution of this equation. There is no solution for this equation. So saying to be, let's say we will generate a number. So it's how it is actually came. So saying to be x square is equal to -1. So there is a number, let's say, of this case where we are doing it. So if you are squaring them, we are getting -1. So let's say that is your I. So if you are if I will do I square, I will get -1 iota. This is your iota I. So I means nothing but your positive root, if you can say, or positive root of for the time. So if it is a square of it, it is going to be -1. So defining to be iota, I mean, best thing is if your I is, I am saying, means I square is -1. That's all. So from here the complex numbers start shaping, and so the solution of this equation is saying to be the I is there, so or plus minus I is there. So now here is different number came now saying to be, if you have a real number 5, then I is there, and then 3 is there. So complex number are now slowly represented like this: a plus ip, where a is a real number, b is a real number, and I is your meaning of I square is equal to -1. Now you get this representation of a number which is a complex number. It is called, where this portion is called, let's say this is your number z, complex number z. So a is your real z, and this is called imaginary z. So this is called your real part, and this is called your imaginary part. Okay. So here it's now usually take the different thing is that now see that real numbers can be represented like just a line, and these are the numbers. But for the complex, see, we need two arguments. One is a, and then second argument is b. This is one real number, this is another real number. This is called real part, and this is called imaginary part. So to present a complex number, we needed two real lines, and saying to be, if here is a and this is your imaginary line part, so this portion is your b. So a complex number represented like in a plane, and this is your called complex plane, and a number here is representing a plus ib. So for reals, we generally use lines, but for complex, we needed two arguments. So that's why for reals, we don't need any argument. Sorry, only one argument, right? 3, 5, -5, 2, whatever. But for complex, see, we have needed two arguments there. One is A and another one is B. So we needed two things somewhere. So this is relating to the coordinate system. If somewhere we have seen this. So this is very much to a coordinate system, but there you have seen a coordinate system is representing a point A, comma B. It not says the relation A plus IP. So complex number, a slightly difference is there in the coordinate and the complex plane. It says your relation between this A and B. And in the coordinate system, it just represent a point. There is no relation between A and B. So it's behave like coordinates. It's look like a coordinate system, but it is not, because there is a relation between these two coordinates. But in the coordinate system, there is no relation. And not only this one, so many things are in the complex now. Slowly it comes to, saying to be even this case also. There is one meaning of it, absolute value. It came actually of this case. So there is first to say that, let's say I have this complex number. So there is a conjugate, it is called Z over bar is there. So which is saying to be A plus IP, sorry, A minus IP. Where the arguments are same, but here is the negative is there. Or if you see it, how it's look like. So let's say here is A plus IB. So here is your B and here is A. So just shift to, same absolute to the negative imaginary. So here is minus B. So it is called the kind of, you are taking the image with respect to x-axis or real with respect to real this real object, the real part. So this is called conjugate. Conjugates are actually, you can say, the image as taken in the real z part, real axis part, and it is that. So conjugate is of this case. So once we came this one, so we thought, okay, what is going to be then the case is, what is going to be here? The case is z into z conjugate. So slowly operations are started thinking, okay, what is going to be this case? So operations are also there. Slowly operations started defining, saying to be, let's say Z1 is A1 plus IB1. So Z2A plus A2 plus IB2. So how the operations is defined, that adding, or you want to find the Z1 plus Z2. So add this real part separately, add this imaginary part separately. So this is A1 plus A2 plus IB1 plus B2. So this is how the operations addition is defined. Multiplication is as usual. You use today A plus B and C plus D. You have to usually do like AC plus AD plus BC plus BD. This is how you used to do. So you can usually follow that procedure to do the multiplication. So what is going to be the case when it is A Z tangent conjugate will do? So if you do it, it will be A square plus B square. This is one.
Yes, sir.
So this tells you kind of, there is no I. So now the absolute also start taking shape, now saying to be, if you root of that thing, this is going to be root of A square or B square, or unconjugate absolute is going to be Z into Z bar square, or Z square is equal to absolute of Z square. So these are some you can see it, and I have discussed when we are taking sessions in great detail. So these are some complex number. These are the complex plane is there. These are some operations we have. Not only this one, there is one also thing is there. Theta angle is there. So here is, let's say I have this one. What is going to be the angle? What is how we'll get that? Thinking to be in the polar coordinates also. We have studied polar coordinates. Polar coordinates is, I think, now it will come. So polar coordinate is one thing is there. What is a polar coordinate? Polar coordinate is if you have a point x1, y1. Okay. So this is in coordinate system. can we think this coordinate to be distance, how much I went there, and the angle with respect to this. So distance r and this angle theta. Still we can represent any point with respect to r, the distance from origin, and the angle made with the x-axis. So this is called the polar representation, representing the coordinate as the distance from origin and the angle with respect to x. By this way, you can represent all any point in the coordinate system. This is called the polar representation. And how we'll get this theta? This theta is, you know, right, how to get that. You know how to find the slope of a line. So by that way, you can say, or mean to say tan theta is equal to y by x. You know, if you remember that slope, which is tan theta. Tan theta is y2 minus y1 upon x2 minus x1. So here is saying to be 0, 0 is another point. So by this way, you can say y by x. So then by the argument, you can find like this using this theta is by this way. And r is nothing but the distance of x square plus y square. So means changing the coordinate in the polar system. So similarly, this way also you can know this is nothing but a comma b, where the representing a plus ib, you can for the timing you can think like this also. So any point you can represent like this also in the polar coordinate. So this is not so tough, but these are some relations. So is this clear? Not clear. I'm just recapping. Okay.
Yes, Professor.
Yes. Okay. So these are the in this, I think in 2 lectures it is. Okay, there is a polar also there. We'll back to that point. Some arithmetics or complex number within these 2 lectures it is there. Complex plane is also unit circle, angles in radians. So these are angles in radian is thinking to be, you know, theta you have. How much theta? So this is angle. Let's say I have this circle. So this is the, let's say I have this circle. Let's say here it is R1 or no, not your. Let's say this point is A. So if it is this angle, this is the theta we have. So how we can convert? So this is in degree, no? This is degree you can convert slowly to. This is whole degree is on a point you can make at most 360 degree. Most this is it. But how we can convert this into radian? This is another gauging, another form of gauging, you know, degree. Sorry, angle, which is called radian. So how we can think that? That is your gauging degree in the different unit. That is, this is in degree, but gauging that in the radian. So converting that is, we can discuss the professor how it is, but I am just writing the simple formula. You know, from starting, this is from when you started calculating. I think 90 standard it started how to convert a degree to radian, saying to be pi upon if you have any angle theta. So you can convert to in radian is theta into pi upon 180. And you can whatever the cancel out, theta pi upon 180. So how it's generated, you can see in the angles. It's not a big deal. These are actually theories. These are not so things. It's actually how the radian came is from this circle. Okay, it came from circle, or you can say it this the full degrees. This perimeter, this perimeter is, if you think it, if you have this circle, if perimeter of this half circle is what is going to be pi r. Generally the full is 2 pi r, we know. Okay, and the half perimeter is going to be just pi r. Okay. And if you see the how much angle it's becoming, this is becoming 180. 180. Okay, this is a 180 degree it's becoming. So if you say, if this whole thing is 180 degree, if you see, let me change the color here. If you see this whole is 180 degree, so how much this portion, how much this theta is there? So if you see this whole one with this pi r is this one, this perimeter, half perimeter is saying to be 180 degree. This makes an angle 180 degree. So how much this theta make? Can we think it in the radian format? That's how the gauging the radian came. So if this is the full is 180, and let's say this portion is this is x, or even this portion is, or this, so, or mean to say how much then it is going to be in the case of this is, or let's say this is a whole is pi r, which make the a kind of 180 degree, kind of 180 degree. So what is going to be for the for one case, or mean to say very smaller portion, or let's say, or how much I will say, uh, 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 for a very smaller portion. This is actually started from by this case, that if it is there is a relation of between theta and this length of the curve. There is a relation in that, and by that way it's actually the 180 pi upon 180 came started to converting that degree. It will be saying to be how multiplying the pi upon 180, or even or simply say that is 180 degree made effect on pi r. So how 1 degree is effect on pi upon r upon 180. Okay. So if you think the radius is 1 in the case of that, and now what is going to be the theta? So theta is going to be pi upon 1 into 180 into theta. This is how actually, so I mean to say 180 degree built by, if you think on the circle, by pi into 1, radius is 1, so 1, just pi. So 1 degree is going to be pi upon 180, and theta is going to be that many times pi upon 180 theta. This is how it's converted in the radian. This is how it's truly converted a degree into radian. So these are some gauging of it, okay, in the from degree to radian. I'm just told you in the layman term. So these are actually covering 3 to 4 lectures, and these are just if you watch the lecture, it will be more just knowing these are the informations. These are the information. Okay, this is what it is. Addition in the complex is, this is what it is. Division, subtraction, conjugates, absolute value. What is a complex plane, unit circle? We all slowly discuss a bit. Let's move to the sinusoidal function, sine functions. Sine. So again, the sine functions is relation we are actually doing on angles. So it's actually came generally from this trigonometric part. This theta, this is angle, how much it's making, A, B, C, it is there. This is A, this is B, this is C. Okay. So the sine functions, how the sinusoidal sine scheme is, we, from the trigonometries given by Pythagoras, from there we know, okay, there is a relation between this angle and this theta is, sine theta is, it's generally give AB upon AC. If you have a fixed theta 30 degree, it will give some value. There is a relation, means, or actually this relation is that is the relation actually can is there, but because of the similarity between the figures, this ratio and upon this one is this one, means I mean this, this whatever the reason, but that's why think of is
Sir, you are not audible.
Sir, your voice is cracking.
Sorry, I just disconnected. Okay, so am I audible clearly now?
Yes, sir.
Okay. Okay, so this is how from the trigonometry actually came the sine functions. Uh, right angle triangle. Generally, you can say now we started thinking it as a variable. So best thing is that knowing to be a kind of this is that this is how slowly the theta is a kind of variable started thinking variable, and this is how it came. Okay. This ratio, and then slowly what is the fixed ratio? That fixed ratio is, see, this is a great deep search done, and then okay, what is the fixed ratio, and then slowly the relation between the angle, it's what's happening, the angle is fixed but still ratio is getting. So this is how the sine theta is generated, that okay, the sine theta is nothing but that ratio, and if angle inputted, we said that okay, the sine value is this one, cos value is this one, and slowly the sine function is developed, sine, cos, and others are developed from these angles. Okay, so it is not even it is related to the circles slowly, like I, as the professor is saying here, he is related to the circle, and then but anyhow, it's making the right angle triangle and how it's related. This is what it's saying, but it's actually related. Came to the going to from the right angle triangle and the ratio and other things, and also from the relations seen. Actually, the relations have been seen from the circles, right angle triangles, chords. Here, what is happening, and the length of the arc. Okay. So, but there are some so these ratios are fixed now, so slowly the other ratios, if slowly angles have been changed, so fixed ratio is came. So like if I change the angle here 45-degree, so again the shape is small or bigger, its ratio is always going to be fixed. So that what is the in that case ratio, so it is going to be root 1 upon root 2. Sine 30 is 1 upon 2, so slowly sine 0 is 0. The simple reason is sine 0 is 0 means there is no angle. If you are thinking this is a 0 angle, so there is no height, it's coming, there is no height is there, so in that case height is 0, and then this portion is whatever the portion exactly, this one means 0, and some non-zero number is going to be 0. So slowly the ratio and other things are developed, and saying to be if it is a 0 30, we are getting the fixed ratio. So similarly we can think the function of this case also. Variables are, what is that? If you have x, or even fx is there, x square plus 2 is there, what is you are substituting? You are thinking a relation. You're substituting the values, are getting relation. So here is 0 is there, 30-degree, 45-degree, 90-degree angle. We know that at most go to the means 360-degree. So can we think this as a variable also? Sine in place, if you assume x is equal to 30, then it becomes sine 30. So what is going to be? So means this is the slowly sine functions are developed, and there are other relations are there. Came now. So sine square, then other relation, I mean to say the cos is also came from the same way the ratio. So you can say we took the in place of taking height and this portion hypotenuse here, in case of this base is started taking, and the ratio of base and this portion hypotenuse. So let's say this is alpha, then b by alpha. This is also is always fixed, and that is also how you can say the cos is, and not other things. When it started developing, so many relations started coming. Then sine square x plus cos square x with the same theta. If angle is same, in that case sine square plus cos square is equal to 1. even I was discussing in the per week I have discussed in the great detail. So let's skip this part, and otherwise how it came, I have fully discussed that how the sine, cos, tan came, all what is the relation between them. I just we want to recap it here. We are recapping. So this is sine 0 is 0, sine 30 is 1 upon 2, sine 45 degrees 1 upon root 2, and sine 90 is right 1. And the reverse, what if the cos is there? Cos 0 is 1, cos 60 is also there. I just missed that. Sorry, sine 60, which is root 3 by 2. And then sine 90 is 1. So other angles now slowly. The cos also, this is 1 upon 3 root by 2. Cos, sine 40 both have the same angle. So cos 45 is also 1 upon root 2. And others are, you can see it. So these are some relations also there. Sine square x plus cos square x is equal to 1, and some angle between some relation in angle is that relation is that sine and the other thing is that sine a plus b is there. I think that is discussed or not, which is sine a into cos b plus cos a into sine b. Some other relations are there between, we have two angles and how it is there. Okay. If you see the graph of sine and cos, as now we are thinking sine functions. So graph is, we graph, as you used to graph the function as simple function. Sine 0 is 0, sine 0 is 0, sine 30 is 1 by 2, sine 40 is 1 upon root 2, sine 90 degrees 1. So here these, if you think, we can think it as an now x as we think in the radian format. We'll think, see, this graph is whatever the graph is, generally, this graph is, your x is in radian. Okay, it is in the radian format. This is from minus pi to pi by 2. Okay, at if 90 degrees you convert in the radian, this is going to be pi by 2. 90 degrees your pi by 2. So this graph of the function, because see, these real numbers are, so what is a radian? You are converting your degree in the real number form. Okay, you are converting your degree in real number form. That is what, no, arc is related to the length, which is a real number. So we converted our degree into thinking at in the real. So radian is thinking to your degree in the real format, real unit. No, the degree is, it is real now. So real number pi, we know pi is going to be some real number 3.14. So in that sense, it is converted into real, and at exactly sine pi by 2, the value is going to be 1. Okay, and at pi, it is going to be, which is 180 degree, and sine 180 degree is 0. So this is going to be 0. Okay. So slowly for minus pi by 2 is there. So in that case, the minus, it achieves the -1. So sine is actually varies from -1 to 1, and again, and after onward, it's back to, like this it we have. So sine function attains the value, but it is a kind of periodic. It's attains a value between 1 and -1. The range of, you can say, sine function is the closed interval 1 to -1 to 1. So if it is this case, then there is an inversibility of, we talk about, as the reason is sine function is for whole r, you cannot, because this function is not 1 1. So we can, in some part, we can talk about the inverse of it. So like minus pi by 2 to pi by 2, the function is 1 1, and not only 1 1, in this portion it is on 2 also. So we can talk about the inverse of it. So inverse of sine function in that region, inverse of sine x is going to be, it is going to be minus pi by 2 to pi by 2. Similarly, cos is there. Cos is, if you see the graph of the cos attend 0, cos 0 is 1 actually. So this is going to be roughly like this. So at pi it is 0, at n at minus pi by 2 it is also 0. And at it is attend minus 1, you can say where it will attain minus 1. Anyone can tell? The cos function where it will attain minus 1. Anyone can answer? Anyone have remember it? Where it attained the minus 1? Am I audible? Anyone can tell where the cos function attained minus 1? At 0 it is 0, at pi by 2, sorry, at 0 it is 1, at pi by 2 it is 0. The next is where it will attain minus 1. 180 degree at pi. So it will tell the minus 1 at pi, which is 180 degree. So means again it is also kind of periodic. So we can think the inverse of the cos is within this range. So these are some inverse of it. Okay, so and there are some derivatives. So let's do some problem. I think I have better to discuss some problem. The polar coordinate, it's fine. It's Euler came now. Next we'll discuss the Euler thing. Inverse we are already discussing. So like there is some relation between the sine cos also, what we have discussed. Now in the mixing form, I'm just saying to be sine s sine 2 theta. We have a cos theta, and derivative will back to the derivative. So these are the sine functions. These are some values are there, and there are some derivative. So derivative of the, once we have a function, we talk about the derivative. We have sine function. So derivative of sine is going to be cos, and derivative if you have a cos function, if you have a cos function, so in that case derivative is going to be minus sine. And there is also a relation that tan x is there, which is you can say sine by sine x upon cos x. And the graph of this tan is, if you see the graph, slowly it is also ranging from minus 1 to 1, but here the range is not, sorry, it's ranging from minus pi by 2 to pi by 2. Okay, but so the outputs are not bounded between minus 1. It will go to minus infinity to plus infinity. It will go to minus infinity to plus infinity. The simple region is also, you can see here is sine is actually take between minus 1 to 1, and cos also take between minus 1 to 1. So if sine is 1 and cos is very close to 0, then range is going to, then 1 upon 0, 1 upon very small number is generally, very large number. So by that way, tan is a of division of sine and cos. So that's why the one reason is saying to be tan have the range minus infinity to infinity is because of this, because of tending with sine and cos, because it is written in upon of sine x and sine x upon cos x. If you think sine as just 1 and cos is very close to 0, very small number, 0.00009. So in the reward form, it is going to be a very large number, right? Some large number it is, which is, already the tan, tan is written that way. So that's why the reason tan attains minus infinity to infinity is saying to be because of it's written at sine and cos. Okay. And the derivative of tan is, we have a tan function, the derivative of tan is going to be sec square x. So there are, which is sec is your 1 upon cos x. So there is another relation also, sec square 1 plus tan square theta is equal to sec square theta. Sin square theta plus cos square theta is equal to 1. These are some relation, these are some angles, these are inverses. The inverse of tan x, which is tan inverse x. Its take values minus infinity to infinity, the range one, and give the input minus pi by 2 to pi by 2, right? That is the inverse property we have. Hence, its take the range, it will, domain is minus infinity to infinity, and output is minus pi by 2 to pi by 2. So even here is also, you can make it open. So these are some inverses, inverse function. The tan, the graph of, you want to say the, see the tan graph is I somewhere made, I made it here, this one. So these are the inverse function, these are the trigonometric functions. Okay. So, and the derivative of these functions are this, can recall it this. So there is some relation also, that what is going to be this sine 2 theta. So you, how we can get sine 2 theta? What is a sine theta? So this could be, came from, you know, sine A plus B is going to be sine A cos B plus cos A into sine B. So by that way, A, you can take A as theta, and B also you can take theta, so that will become 2 theta. So this is going to be sine theta into cos theta plus cos theta into sine theta, which is of case, which is the case of sine. Both are same, so this is added sine theta to cos theta. Similarly, other properties is cos 2 theta we have. So what is going to be cos 2 theta? So you can get from, you have one thing, sine square theta plus cos square theta is equal to 1. So cos square theta is equal to 1 minus sine square theta. So can we use this to get this one? No. Let's use the other identities, which is cos of A plus B, which is cos A into cos B minus sin A into sin B. This is for the cos A plus B. Cos, similarly, A minus B is there also, you can get, which is cos A into cos B plus sin A into sin B. So these are identities. You have to remember it, because using these identities, we have one problem on it. See this problem. If you have a cos theta is equal to this one, what, find the value of sine 2 theta? Anyone can solve and let me know what is going to be sine 2 theta. If you have cos theta is this one, what is going to be sine 2 theta? Anyone can tell? So almost done. I have just recall all, some one or two problem is there. This is a single problem. We'll discuss this. Anyone can tell what is sine 2 theta? No? Okay. So you can easily get by, you know, This is cos theta. So using this property, just we wrote now, whatever the cos theta. We have to get the, if you have a cos theta, we can easily get sin theta, right? Sin square theta plus cos square theta is equal to 1. So sin square theta, we want to get it. So let's write sin square theta plus cos square is 1 upon root 5, which is 5 is equal to 1. So sin square theta we will get here 1 minus 1 by 5, which is 4 by 5. So sin theta is going to be, or even once we got the sin square theta, so sin 2 theta is sin theta into cos theta. And sin square theta is 4 by 5. So sin theta is just going to be root 4 2 upon root 5. So sorry, here is 2 is there. So 2 sin theta. Sin theta is 2 upon root 5 and cos theta is 1 upon root 5, which is 2 upon 5. So using some identities here, you can just derivate it and then substitute, get it. So these are some identities. Oh, I just missed that Euler one. So Euler is simple one reason. If you have e power I theta, you can write like this: cos theta plus I sin theta. This is your Euler formula. This is the relation between e power I theta and the sine and cos. E power I theta is equal to cos theta plus I sin theta. This is the Euler formula. And using that, we can get the cos theta, we can get the sine theta. How we can get easily? From here, we can think e power minus I theta, right? E power minus I theta is cos theta minus I sine theta. Now, if you add these two, it will give, if you add this equation and this equation, it will be I theta plus e power minus I theta. This will be cos 2 theta. Sorry, cos 2 cos theta. So cos theta is going to be e power I theta plus e power minus I theta upon. So similarly, sin theta also you can get, which is just e power I theta minus e power minus I theta upon. So sin in Euler exponential form also we can get it. So these are, this is the only in Euler form. And that's all the week 10 is there. Anyone wants to say something? Answer is 4 by 5. Yes, yes. NK, what is your name?
Sir,
Hmm.
sir, hello, sir. Am I audible?
Yes, yes, you're audible.
Sir, actually, I've managed to clear qualifier level,
Mm-hmm.
but I'm not sure how to register to foundation course. It is showing that I am eligible to register, but I'm not sure where to register. I've
So
mailed
it
a
will
couple
show
of
in your
times.
portal, no? It will show it in your portal that register which course you want to register. It will give the option.
Where is that option, sir? If will it be in the dashboard itself, or I should go to every course and register?
No, it will be in the dashboard, right? Anyone can answer it. It's from a student side. Iram, Susmana. Anyone, Amit? Anyone can answer this. How you register? It will be in the portal. It will be in the whatever the portal you got, right?
Actually, I don't have the idea because I have taken the entry through the J route, so I can
Okay.
say how the qualified students get entry.
Anyone is here from normal without JE? Actually, you know, once you open it, it will be, even I have the access of this. So even whatever you have dashboard, in the dashboard you will get the options of register the course.
Okay, sir. Like it will be like a link, or I can register directly.
uh, on the somewhere dashboard it will be shown that register the course, the course's name would be given, and just you click on that to register. This is how it will go. So it's not showing in your portal, is it? Have
Yeah, sir,
you?
no, sir, it is showing that I'm eligible, but I'm not sure where to register. No links or so and so is provided for me.
So how you are looking the content then?
No, sir, the courses are uh, there, like four courses are there, but
Mm-hmm.
I don't know where to register for foundation.
No, so how you are attending this, how you are completing this maths, and then after the qualifying, you're able to proceed, right? After the registration. Without that, you cannot see the head week score content.
I don't know, sir, because up till week 12 I have completed.
Okay.
So I'm not sure what I should do. I have mailed the support team like couple of times, but no
Mm.
response still.
Okay.
I'll check another time, sir. I'll check another time if there is something
Okay.
I can do.
Actually, it will be in the portal. You don't need to go anywhere. You will just, everything is in a portal. It will be available in portal somewhere on the corners, or click there. It will show the option, just register. It will see the list of courses which will be offered for you, and then you have to register the course. This is how it is generally in a portal.
Okay, sir.
Okay,
Okay, sir.
okay,
Thank you,
that's
sir.
all in the revision case. Okay, thanks, Brian. Thanks for joining. Okay, we'll see you in the next revision session.